With all the background that we currently have, we should now take a look at the idea of independence. Now, two events are said to be independent if the occurrence of one does not does not have an effect on the probability of the other event occurring. Now, let's take look at a couple of obvious examples that don't involve a type of calculation. Event A, my truck is gray. Event B, I like ribeye steaks. Now, is the fact that I have a gray truck, knowing that, if you knew that I drove a gray truck, would that tell you anything about the probability that I happen to like ribeye steaks? No, there's no connection there. There's totally two independent events. One event happening offers no information about the other. My dog ate the rose bush. Okay? That's one event. Today is Monday. That's another event. If I told you either today is Monday or if I told you my dog ate the rose bush, would that help you figure out the other? If I said, hey, my dog just ate the rose bush, would that help you figure out what day of the week it is? No. If I told you, hey, today is Monday, would you have any clue if my dog just ate the rose bush or not? No, those two events are completely independent of each other. One happening has absolutely no bearing whatsoever on the other happening. So let's formalize this a little bit more with the idea of probabilities. So let's consider two arbitrary events, events A and B. If A and B are independent, then the fact that B just occurred will not have any effect on the probability of A occurring. That's why I just got done saying. So the additional knowledge of B occurring has no effect on A. This suggests that the conditional probability A given B, will simply be the probability of A, because knowing B happened has no effect on A. A is still what it always used to be. This relationship gives us a nice way for checking for independence. Because if I can find the conditional probability and I can find the independent probability, I shouldn't say independent, the probability of the individual event A, if these two happen to be equal, then the events A and B must be independent. So that's a quick way to check. So for this to be true, the probability of A given B is equal to the probability of A and B divided by the probability of B. We already saw that. We already saw this idea on a conditional probability. Therefore, for this to be true, A and B must equal A times B. By saying this, I mean this to be true. So the only way that the probability of A given B is equal to the probability of A, the only way that can happen is if and only if, that's an IFF, it's common mathematical notation for if and only if, the probability of A and B is equal to the probability of A times the probability of B. That's the only way that can happen. Why? Let's go back up to this. If this is true, what I have is the probability of A times the probability of B divided by the probability of B. That will allow me to cancel these two probabilities and give me the probability of A. That's the only way I can get the probability of A out of this. That's the only way that this joint probability will in fact be equal to the probability of A. And that can only happen, if A and B are independent. Well, that just gave us another nice way to check to see if something is independent or two events are independent. Because we know if independent, then number one, the probability of A given B must be equal to simply the probability of A. So if I have a way to check for these two probabilities to see if they're equal, I'm there. Number two, we know the probability of A and B must be equal to the probability of A times the probability of B. That's only way, this is the only way this can happen. So actually we can check both of these. If there's a way for me to find the joint probability, A and B, and the individual probabilities, all I have to do is multiply and see if these guys are equal. If they are, I can right away conclude that they're independent. Likewise, if I can find the conditional probability and compare it to the individual probability of A, then right away I know that A and B are independent. Now this flip-flops too. If A or B are independent, that would also imply that the probability of B given A must be equal to the probability of B. And still, the probability of B and A is actually the same thing as the probability of A and B, which equals the probability of B times the probability of A, which is obviously the same as the probability of A times the probability of B. Now, all of this is if and only if A, B are independent. If they're not independent, this won't be true. Now, let's go back to this table that we've been working with. Are the events freshmen and more than 20 independent? Well, right away, the tendency, the gut feeling would be to immediately say yes or no. You may have a gut feeling. Don't use your gut feeling. Bad idea. We have values here, so we can actually calculate the probabilities here. And based on what we just talked about, we can make the determination if, in fact, they are independent or not. So, the probability of freshmen given more than 20 equals probability of freshmen if independent. If independent, we know this is true. Well, what's this probability? Freshmen given more than 20. Well, more than 20 is right here. So given. Here's freshmen. They share 17. This is 17 out of 104. This must be equal to the probability of freshmen if independent. So I'm going to assume they are independent, check them, and then say, hey, I was either right or wrong. Well, the probability of the freshman is 66 out of 280. Now, you can reduce this to a decimal and compare them, but I recommend that you don't do that. Cross multiply, and this is true if and only if 17 times 280 is equal to 104 times 66. Now, if you grab a calculator, you can see quickly that they're not. And actually, you don't have to grab a calculator in this one, because 7 times 0 is 0. So I know when I multiply this out, I'm going to have a 0 in the ones place. 4 times 6 is 24. I know I'm going to have a 4 in the ones place here. These won't match. So what I know is that these are not equal. These are not equal. Therefore, they are not independent. And if not independent, we say they are dependent. There are only two possible things that could happen. Either they're independent or they're dependent. Not independent means they are dependent. Now, if this is kind of driving you nuts, you grab a calculator here and you see that this value is actually going to be 4760. See, there's the 0 I was talking about. And this value would be 6864. There's the 4 I'm talking about. So I knew if the ones didn't match, I didn't really care what happened elsewhere. They're not going to be equal. Okay, let's take a look at another example. School administrators were proposing a change in the academic calendar year. 60 students were surveyed and asked if they preferred option A, which is a shorter Christmas break by 1 week that would result in a longer summer break, or option B, a longer Christmas break by 1 week, which would result in a shorter summer break by 1 week. So they surveyed 60 students, freshmen, sophomores, juniors, and seniors, and option A and option B, and this is what they said. So I have this table here. Now, are the events senior and option A independent? Well, here's senior, and here's option A. Well, if they are independent, then we know that this must be true. If they're independent, this must be true. So let's just check to see if it's true. A probability of senior given option A. Well, given option A, I'm right here. That's 4 out of 20. Now this must be equal to the probability of a senior. Well, the senior is 9 out of 60. So here again, if I quickly cross multiply, I'll get 4 times 60 must be equal to 9 times 20. Well, 4 times 60 is 240. 9 times 20 is 180. It's my little trick of the zeros, or look at the ones place didn't work because I get 0 in both places. These are not equal. Therefore, they're not independent. They are dependent. If dependent, that simply means that knowing that one happened, it changes the probability of the other. It has an effect on the probability of the other. Are the events freshman and option A independent? Well, let's take a look here. Let's go back up. Freshman and option A. Well, if they are independent, then we know that the probability of freshman given A must be equal to the probability of freshman. Well, the freshman given A happened, there's 20. Freshman, there's 5. So that's going to be 5 out of 20. That must be equal to the probability of freshman if, in fact, they're independent. Whoops. Well, the probability of freshmen is there's 15 freshmen out of 60. So this is 15 out of 60. And what you end up with is 5 times 60 must be equal to 15 times 20. 5 times 60 is 300. That must be equal to 15 times 20. That's also 300. Check. They are equal. Therefore, they are independent. So knowing the fact that the person was a freshman doesn't tell you anything about option A. And likewise, knowing the fact that they chose option A doesn't tell you anything about them being a freshman. These two events are independent. If F is independent of A, then it's also true that A is independent of F. It goes both ways.